Good morning, everybody. I am very, very sorry that I am not there in person, though I will be available to answer questions on Zoom immediately after this. But I hope to share with you some work that we've been doing on characterizing the amounts and impacts of anomalous freshwater from the melting ice sheets and shelves on the ocean and on the climate. I just want to say right at the beginning that this is very much a group project. It isn't me alone. Ken Mankoff did most of the pulling together of all of the data, and there have been huge amounts of back and forths and discussions with the whole group that I will introduce a little bit later. Anyway, so with no further ado, some background. We are probably all aware that the last round of climate models, CMIP6, are not matching some key trends in the ocean, particularly in the sea surface temperatures, particularly in the eastern tropical Pacific, where the real world seems to be more La Nina-like in its changes than the models are projecting. But the other big place where there's a large discrepancy in the trends is in the Southern Ocean. And you can see that very clearly, the blue part in the ERSST dataset compared to what we're seeing in the multi-model trends. There is muted warming there, but there is no real overall cooling. There are also mismatches in things like regional sea level rise. So this is the sea level rise that you get after removing the global mean, and you can see that the pattern there is obviously affected as well in the tropical Pacific by ENSO dynamics, but there are also quite clear uncertainties or differences with the pattern as seen in various models. This is just one model from the GIS CMIP6 effort, but there are these things go across all of the different models. We know, of course, and we've discussed this here in this meeting already, that ice sheet mass is decreasing both in Antarctica and in Greenland. That's the grounded ice mass loss is being tracked by GRACE and the GRACE follow-on missions, and while there has been some ups and downs, there's been a pretty steady decline in both hemispheres to the tune of hundreds of gigatons per year of additional water that is going into the oceans surrounding those ice sheets. We know also that the ice shelves have thinned. We know that from altimetry data, and that is a loss of fresh water from the cryosphere that is also going into the ocean. It doesn't have as much of an effect on sea level, nothing like as much of an effect on sea level, but it's still a freshwater input into the surface ocean around the continents, and is having an impact on salinity and stratification and the like. And we know as well that the ice shelves themselves are retreating. So you have additional mass loss from the ice shelves through calving events. Now, calving is more episodic. You often get a big calving event and then a slow regrowth and then a big calving event. In steady state, you would expect to see that kind of pattern, but we're not in steady state. The ice shelves are in the mean retreating, though not everywhere and not all at the same time. So the question that we have to answer is, well, are these freshwater anomalies, the differences from some assumed steady state, are they large enough to matter to anything outside of the ice shelves themselves? And the answer appears to be yes. So in work that we did and published a couple of years ago, we took what we thought were reasonable estimates of the loss of grounded ice and the loss of floating ice sheets, ice shelf ice, and we put that into the model that we had, the GIS CMIP6 model, with the time series that you can see above, and you know, and these are numbers that get to over the last 20-30 years, tens of thousands of gigatons of fresh water going into the system. and we distributed that fresh water in a rather, I would say, naive way now, and we distributed it as ice over the top of the ocean. Does that have an effect on the climate? And the answer is yes, it does. It has an effect both on the climate and on the trends. And so what you see are impacts to sea surface temperatures. So you see cooling in the Southern Ocean, you see cooling in the North Atlantic, you see freshening, particularly in the Southern Ocean and in the North Atlantic. You see sea ice concentration changes, particularly an increase in sea ice around Antarctica, and in the Arctic, the sea ice change is kind of balanced between an increase in sea ice in the northern North Atlantic and a slight decrease in sea ice in the Pacific sector. And there are also impacts on regional sea level rise because of that additional steric effect from that additional fresh water. Particularly, you see an increase in sea level around Antarctica and changes associated with the O-turn extreme function in the North Atlantic. On the back of that, we organized a workshop in February 2024 to really see if we could not do a better job. The idea was to pull together more detailed information, more resolved information. What could we say? How should we implement these things in models? And that was it was eye-opening because it turns out that there was a lot more information than we had used up until then, and it also was that there were a lot more ways in which people were using this information or could use this information than we had initially envisaged. This was we were trying to do this in a hurry to support the CMIP 7 preparation efforts, and so we decided to do this entirely online with participants from every continent, including Antarctica, with a few sessions where we tried to get everybody to show up for an hour, but then with asynchronous discussion groups, and everybody who gave a talk did it like this, using video, a pre-recorded video, so that people could watch it before we had to discuss it and at a time that was convenient for them. So that was both interesting to organize, and I think there's a few of people who participated in that who are here this week as well. And we actually wrote that up as something that people could learn from. We did a lot of good things, but I think we rushed things a little bit more than they should have been rushed. We should have spaced it out a little bit more. But if you're interested in trying to run virtual global workshops, the QR code there will take you directly to that article, and there are a bunch of lessons learned, tips and tools that people could use to do their own efforts. And I, given that travel is somewhat constrained for some people at this particular moment, I am very pro people doing virtual workshops, but in a way that really brings people in and helps them interact as deeply and as effectively as they can. So last chance there for the QR code. And okay, back to the main programming. So what did we want to do at this workshop? So we wanted to really understand where this anomalous freshwater is being delivered and how it's being delivered into the ocean. There are differences in both Greenland and Antarctica, but we're trying to, kind of do something that works for all ice sheets and even ice sheets that existed in the past. And we're trying to understand what all of the different processes are and how to characterize those, and importantly, how to build a time series of these things that go back over the historical period, so that we can use them within the historical simulations for the CMIP 7 simulations. So there are, I don't need to go over all the different processes. We've heard from many people this week how complicated and how uncertain some of them are. And so I'm going to try and average over a lot of that uncertainty, but acknowledging that there is deep uncertainty in many of the net effects of these different processes. I love this diagram. This is from a new paper by Ken Mankoff. It's really like the full mass balance for the ice sheets. What's coming in, what gets recycled, what is being taken from the stock and lost to the ocean, and all the different ways in which mass is coming from the ice shelves and continents. We are trying to characterize each of those elements. This is obviously for the climatological average, and I'll get to why we're only interested. Well, we're mostly interested in the anomaly from the climatological average in a second. But looking at the retreat terms and the changes in calving, the changes in basal melt, those are the key elements that we will need, or that we're trying to characterize and quantify for use within the models. So the first thing that we did just prior to the workshop was we actually asked the modeling groups what it was that they were doing now, or so what they had done effectively in CMIP 6, and there was a huge amount of variation. People have different conceptual models for the ocean. Are they mass conserving or are they volume conserving? That makes a difference to how you plug in the fresh water as a boundary condition. Some models did not even attempt to close the water mass budget. So when snow fell on the ice sheets, they didn't really worry about that snow coming back into the model. And so there are 2 of the 16 models that talked to us said that they did not keep track of any freshwater fluxes coming from Antarctica or from Greenland. That is not a choice that I would have made, but I understand why people do it. But it does mean that some models are very unlikely to be able to capture the impacts of changes in those freshwater fluxes if they don't have any freshwater fluxes to start with. There was more variability in how the energy budget was closed, whether people took account of the latent heat of the snow that was falling and putting that back into the ocean. Some groups did a very good job, some groups did an okay job, and other groups ignored that altogether. That's the kind of thing that kind of gets resolved in the global top of the atmosphere energy balance. It's not a very large term, but it is the kind of thing that I worry about a little bit when you come to trying to calculate the impacts of relatively small radiative forcings. The big surprise to me was the split among the ocean modeling groups for what they did in the historical runs. So almost all of the models calculated how much water was going, how much snow was going onto the ice sheets that was not being put back into the ocean because they didn't have interactive ice sheets. None of these models had interactive ice sheets. And so some people calculated that at the pre-industrial control, so for the mid-19th century, and kept it fixed for the whole of the historical period. And other groups, including ours, assumed that the ice sheets were always going to be in mass balance, and therefore adjusted the fluxes to maintain the mass balance of the ice sheets. Now, when the ice sheets were in mass balance, that was a fine assumption. In fact, if they were in mass balance, then a fixed discharge would also be a fine assumption. But when there is an imbalance, and we've clearly seen that there is now an imbalance in the ice sheets, the consequences of those 2 choices are quite different. So one of those choices means that you don't get the increase in fluxes. The other one assumes that the fluxes change in order to maintain mass balance, and so neither of them are going to give you anything like the right answer. And in fact, they both get one hemisphere very wrong, and they get a slightly better, do a better job with the other hemisphere, but it's different hemispheres for different approaches. The other things that folks varied on a lot is what happens to iceberg melt. Does that get spread spatially? Does it get calculated? Does it get just kind of put in globally? And so there were at least 4 or 5 different ways that that groups are doing that. I think pre-calculated maps is a good way to go. Lagrangian icebergs is good if you have sufficient ocean resolution to really push them around appropriately. And then some groups did nothing. Notably, none of the ocean models in CMIP6 included ice shelf cavities in their ocean model, and so the edge of the ocean model is at the ice shelf front in Antarctica, or at the fjord edge in Greenland, and that has some consequences later on as we go forward. So the first thing that we did and that we realized is that we can do a better job than just like one number per ice sheet. We can actually calculate fluxes, imbalances for each of the major ice sheds, major ice basins across the continents. So there are 18 basins that have been highlighted in previous work by IMBY in Antarctica. There are 7 basins in Greenland that have been highlighted by work by Mugino and Rigno. And so we've decided to actually calculate all of the time series and impacts specifically for each of those different regions, because we can think of each of those different regions as being an independent ice sheet over the time period that we are looking at. One of the things that we have been able to do is to take high resolution ocean models with Lagrangian icebergs and then map out where the icebergs go from each of those different regions. And so instead of just having one map for all icebergs regardless of whereabouts they originate, we now have in Greenland we have 7 maps for each of for icebergs that come from each of the different regions. And you can see, for things that are on the west of Greenland, you have more of a distribution on the west in the Labrador Sea. For icebergs that are coming off the east of Greenland, then again, you have a kind of a more easterly melt pattern, and you can see some details there. In Antarctica, because of the circumpolar currents, almost all of the icebergs almost always end up in the Weddell Sea or coming out past the Antarctic Peninsula, and so there's a little bit less variation. Obviously, icebergs that come directly from the peninsula really only stay there, but icebergs that are coming from pretty much everywhere else around Antarctica will eventually end up in the Weddell Sea and in the southern Atlantic sector. But we can again calculate the maps for each of the different regions independently. So that's a big advance over anything that people have done before. We can then calculate using a combination of data, right? So this is including surface mass balance estimates from regional models, MAR, RACMO, and the like, discharge observations from in situ and from visible remote sensing, and we can do that to about the 1990s. We have individual independent estimates from each of the ice basins in Greenland, and then going backwards we have net amounts that we then distributed evenly or proportionately across the basins going back in time. Because of our ability to do the surface mass balance all the way back to the 19th century, with reasonable caveats, we can then produce a time series of absolute discharge for each of the Greenland regions, and then we can calculate the anomalous fluxes, assuming that the 19th century period was relatively quasi-stable and can be assumed to be in steady state. And so we can calculate in Greenland the anomalous fluxes in discharge over that whole period, which is great. In Antarctica, we do not have that luxury. Obviously, if you go back too far, we don't really know what the surface mass balance was. We don't have the constraints on the weather or the sea ice or anything like that, and so we are somewhat limited. And so we really only have data for the Antarctic components from about 1990 onwards. And so the anomalies that we're defining for Antarctica are with respect to 1990, effectively. And so if you think that 1990 was in steady state, then that's fine. Then these are true anomalies. But if you think that 1990 the ice sheets were already not in balance, then there's going to be a missing component to this going forward. And that's something that one would hope to be able to do a better job with later on. But for the time being, that's as good as it can get. The other thing that we need to work out is how to distribute that discharge among the different elements, right? So how much of that discharge goes into icebergs that then move away from the local area? How much of that discharge is submarine melt that's kind of underneath the ice shelf that's coming in at the bottom of the ice shelf that could be hundreds of meters depth? How much of this is frontal melt that is really just kind of coming in right at the surface in the melange? And where do we draw the boundary, right? So in high-resolution coastal oceanography, then you're going to resolve all of these things. But in the climate models, you often don't resolve any of these things. As I mentioned, in CMIP6, no models had ice shelf cavities, and so the boundary of the ocean model was at the ice shelf front in most of Antarctica. And in Greenland, we're not resolving any of the internal fjord dynamics. And so the water that's coming out of the fjord, it's really kind of coming in the mixed layer at the surface, as well as via the fraction of the glaciers, the fraction of the icebergs that come out of the fjord and then drift further afield. These are not hard and fast numbers. We have made pretty rough estimates based on a few field studies that people have done, but we're not going to claim that we know exactly what that split is, and so that is something that we will need to work on collectively moving forward. The implementation of these fluxes is actually pretty subtle. We have, like as I mentioned, there's two main ways that ocean models have done this. They've either assumed that the discharge from the ice sheets was fixed at pre-industrial levels, or that the ice sheets were in mass balance, and so the fluxes would vary as a function of the net surface mass balance that the atmospheric models are calculating. If you want to have something that has the variations that we see, then the changes that we've seen in the observations, you have to add in that anomalous flux somehow, and that's a little bit different depending on which of those choices that you made. And the consequences of those choices are that you can either have fluxes into the ocean that are as observed, but you don't get the mass balance on the ice shelves, and so your total salinity change and your total sea level change is going to be off. or you match the mass balance of the ice sheets and ice shelves, but your fluxes might not be exactly right. These errors arise because the atmospheric models are not able to produce a perfect surface mass balance over time, and so where do those errors end up accumulating is the question, and there's no right answer, and so people, I think, are going to continue to make different choices as they feel. We have a lot of work left to do. There's no question that we could be doing a better job with the iceberg distribution. We could do a better job with the vertical distribution of the freshwater. We could make better estimates of that split in the discharge between local melt, calving, submarine melt, and the like. We haven't included any impacts of grounding line movement, which are hard to account for, but as yet are relatively small. And we are really at the beginning of trying to work out, if you do this for the historical runs and then you want to go on to do scenarios, what should you be doing for the scenarios? And we are talking to the folks at ISMIP to try and see if we can use that information to drive anomalous fluxes going forward. And we have a process that should be proceeding at the moment to try and produce those. There are also questions about what you should do with respect to idealized simulations that you have that are being used for instance for calculating climate sensitivities. Now, one of the things that happens with the impact of the fresh water on the ocean is that it cools, particularly in the Southern Ocean, which is one of the places where there are a lot of cloud feedbacks. And so a cooling Southern Ocean could actually have a non-negligible effect on the calculated climate sensitivity if you could make a clean estimate of how much the ice sheets would melt as a function of, for instance, global or local temperatures and the like. And that's non-trivial, and so it's not obvious how you would calculate the impact of this particular functionality on something like ECS, unless you have the fully interactive ice sheets that would calculate all these things at least physically consistently. Can you do a better job before that happens? That's very unclear. We will see the first idealized simulations with interactive ice sheets within the CMIP process in CMIP 7. The UK ESM model, for instance, is well on its way to doing that. The NCAR model may be able to do some of this as well, and so we will have an estimate of what the delta flux to delta global warming estimates would be, and then we could put that into some of the other models that don't have the interactive ice sheets yet. And of course, if we were to move to paleoclimate regimes, the last glacial maximum, the last interglacial even, the deglaciation, then or the Pliocene, then obviously all of these things would have to be reconfigured and recalculated. That work has not been done, and that is something that I think we would want to do quite quickly once this historical data is put out there. There's one other element which I'm just going to put in here just for completeness, and that is whether you can include mountain glacier fluxes as a forcing. And the reason why you would do that is because at the resolution of the atmospheric models, most mountain glaciers are not being resolved, and the mountains are not high enough really to support that, and that melt, which is clearly having a significant impact on sea level right now, is not being included in most models. So that has implications for water resources. It has implications for soils, rivers, lakes. And we already have estimates of how that's going to change with scenarios. So these are things that can be put directly into models actually pretty quickly. And so we have a paper on that in preparation. So I just want to give a shout out to the paper that describes all of these data sets and protocols. It's currently in open review at GMD. If you click on, well, if you look at that QR code, you can go directly there. We have a couple more weeks of open review, so if you read something there and you want to comment or you want to say how wonderful it is, that would be nice too. There's still time to put in your review. We're doing the revisions with respect to the reviews that we have already right now. But most importantly, the code that created all of these data sets and the data itself, which you could input into your climate models today, should you want to. All of that is already available on Zenodo, and you can just download it and start plugging it in if you are interested. I don't think we're going to get full participation for the CMIP7 historical runs, but I'm hoping that we'll have more than a few models, and that this may in fact be a key additional forcing that we need to think about for models that don't have interactive ice sheets that might help explain some of the mismatches that we saw between the observations and the CMIP6 models. And so I will just leave that up there, and I will pop back via Zoom to answer any questions. And thank you so much for having me here and letting me tell you about this great effort. Thank you.
Okay. Thank you. You turned it down? Appreciate it. Okay, we can treat the microphones normally. Hi, Gavin. You're there. All right, please use the microphones, or if you're in the middle, I can bring it to you for questions.
Yeah, thanks, Gavin. I had Alex Yan, CU Boulder. So yeah, this is really cool and something I've been thinking about for a while of what the influence of that is. I was just wondering if you've looked in the simulation where you've done this, because the meltwater fluxes, they have like a lot of interannual variability, and in the free running models, those won't line up with like the very warm years that might have caused those. Like, do you see like a kind of a real forced response to these meltwater pulses that then like kind of we're like superimposing on all ensemble members?
Yeah, that's an interesting question. In the runs that we've done so far, we didn't have very much of the interannual variability because that's mostly coming from the carving terms, and that was smoothed over. Or actually, I don't think we included it very precisely at all. But that would be that's an interesting issue. To some extent, you expect things to be mixed over a number of years anyway, because of the way the water mixes, because of the way the icebergs melt. And so you might want to think about smoothing some of those interannual variabilities away while maintaining the long-term changes. That's an interesting issue. I mean, it's something that comes up a lot in other contexts, where you have perhaps composition that's driven or that's affected by ENSO, and you've calculated that composition based on AMIT runs, and then you're running it in a couple model, and so you have some portion of the real history in a situation where the model is doing something very different. We've never really noticed anything particular about that in those other contexts, but it'd be interesting to look at here. I don't know what the answer would be. Thank you.
Kevin, thanks. That was a great talk. This is Chloe Chang from Stanford. I was wondering, with the icebergs, the way they were simulated, did that also account for their motion as affected by sea ice? I think somebody brought this up earlier in the conference.
I don't know. Those runs were done by Nicolas Jourdain and Clara Burgard. I think with one of the high resolution EPSL runs. I can investigate. I mean, if you go to the paper, the papers from which this was taken are cited there, so you could dig in and see whether there was a sea iceberg interaction. But I don't know offhand. Interesting question.
Thanks.
Hi, I have a quick question before my question, which is I don't know what time the historical period that you represent begins.
Generally speaking, it's 1850 to as close to the present as we can get. So pre-industrial is nominally 1850, but when we're talking about temperatures and things like that, we've assumed that the period from 1850 to 1900 is a quasi-stable climate point, and so 1850 would be the start of the historical thing. So the data from Greenland, because we have the reanalyses that go back, I think even before that, I think to 1840 or something, they cover the entire historical period for the CMIP runs, but in Antarctica, obviously, that's not possible.
Okay, so my question is, in regards to northern hemisphere glaciers, whether it's Greenland or mountain glaciers, do these reanalyses or do your historical kind of either constant flux or mass balance, how do those kind of consider or treat the end of the Little Ice Age, where you have kind of before anthropogenic warming really kicks in, you have this widespread retreat of ice?
Yeah. So the way that models are run is that they expect everything to be in quasi-equilibrium in 1850 conditions. That is a good approximation, though obviously it is not a perfect approximation. And I'd be looking to the ice sheet modeling community to tell us how off that assumption is for the 1850 to 1900 period. Are there kind of long tails of Tambora, or the prior cooling and the warming up from that? I don't know, but I'd be happy to hear from anybody who's been running ice sheet models over that period, to let us know what is the potential error there. My guess is that it's still pretty small compared to the deltas in the freshwater anomaly by the time you get to the end of the 20th century, and so it's probably not so relevant for looking at historical trends, but it's a valid question.
Hi, Gavin. Great talk. This is
Thank
Becca
you.
Jackson.
Hi.
And I was wondering if you could say a little bit more about, you have the partitioning between local submarine melt and calving, and kind of how it looked like you had two different scenarios, like a 50-50 split,
Right.
maybe a 25-75. And I guess I'm curious both kind of how you chose those numbers, and then also how sensitive you think the simulations are to that partitioning, particularly when you put it sort of in the context of you're looking at the historical, maybe 20% anomaly of freshwater, and then
Right. So I would love to be able to tell you how sensitive anything is to this, but I have no idea. The numbers that we came from are driven from like a few field studies that people have done. The citations are in the paper. Nobody is pretending that we know these numbers very accurately. One would hope that there isn't a huge sensitivity because of the mixing times in the near near shelf circulation. But I mean, like depending on, if you're at the front of the ice shelf, and it's a difference between, water coming in, like 400 meters, 700 meters sometimes, versus water that's kind of coming in at the surface. I mean, that could have significant impacts on local stratification. One of the things that I didn't discuss here, but was discussed yesterday, I think, is the Sophia set of simulations, and they're trying to do things in a more kind of, well, let's break it down. Let's do every one little thing at a time and see how sensitive the models are to that. I'm happy for them to do that, and then they can tell us what we should have done in the first place. But the need to have something ready for CNIP7 I think, overwhelms the need to have it be perfect.
Yeah, it's got to start somewhere. Yeah, for sure.
Yeah.
Thanks for the talk, Gavin. Could you speak a little bit more about differences and what you're doing different from Sophia in the Southern Hemisphere, and how your effort sort of corresponds to it, whether it's complementary, orthogonal?
Yeah.
That sort
Yeah,
of.
no. It's totally complementary. The difference is, it's the same difference that comes up a lot in climate modeling. Do you do something that's simple that everybody can do and then you can compare the models, or do you do something that is more realistic, but everybody's going to do it a little bit differently, but you have a greater chance of matching some observations? And it's a bit of a philosophical discussion, and it comes up a lot in paleoclimate. It comes up a lot in historical things. My predilection, I guess is the right word, is to try and do things as realistically as you can, because the most important comparison is not from one model to another model, but between all the models in the real world. And I think that we have to give the models as many chances to match what actually happened in the real world as we can. Now, other people are, no, we have to understand the models, like we have to understand the sensitivities, we have to understand, and that's a slightly different approach, and I think it is complementary. But if I have to pick one, I pick do the most realistic thing that you can. But the Sophia project, we're contributing, the model that we used in the 2023 paper. We're doing some of the Sophia runs, and so we will be able to do, here's the historical estimates, here's the Sophia runs, like where are there differences, where there are important issues, and that will help revise this protocol going forward. So complementary. Yes.
Okay, thanks. If I may sort of follow up, since you brought up an issue, and actually what we've seen in the past several days, that high resolution models do completely different things from low resolution models. Mm-hmm. So in that regard, if all models try to do the same, but some of them are 1 degree models versus 1/10, 1/12, how are you going to reconcile those differences associated with the behavior of the models per se? Thanks.
Yeah, I mean, I don't need to reconcile them at all. Different models have different processes and have different mixing, and some of them have, different cloud feedbacks that might be right, might be wrong. And they're going to be differently sensitive. The key with setting up the freshwater as a forcing, right, because we don't have the interactive ice sheets, our idea is that no, like if something is actually happening, if something is actually impacting the ocean, then we should put it in, right? If you get the right answer for the wrong reason, then that's not helping us, right? So if indeed the freshwater amounts, and I think they are, the historical freshwater amounts are sufficient to be impacting stratification, sea ice, and the like, then we should do it, and we should do it with the high resolution models. We should do it with the medium resolution models. We should do it with all the models, right? It's a real forcing that if we want to compare things to the real world, we need to include.
All right. Thank you very much, Gavin, for joining us online. I think we're going to move on to the next speaker.
Bye.